One of the uses for the Programmable Gain Amplifier, or PGA for short, and the ATtiny1627 family of microcontrollers is to interface with sensors and signals that are ordinarily too small for most ADCs to measure. Application Note 3641 uses this feature to interface with a passive infrared sensor, or PIR, to detect motion. The PIR sensor's output voltage is a function of the infrared light hitting the sensor. As a being or object enters or exits the sensor's field of view, the amount of infrared light hitting the sensor changes, and thus the output voltage. However, the PIR sensor's output has a DC bias, which would make measurements with a standard single-ended ADC difficult due to the offset. To remove this offset from the measurement, the ADC on the ATtiny1627 family of microcontrollers was used in differential mode, where the signals are subtracted, leaving only the difference between them. MPLAB MINDI analog simulator was used to simulate the passive RC low-pass filters used with the PIR sensor. This graph shows a 1 Hz sine wave with an AC amplitude of 1 mV on an 800 mV DC common mode voltage. To create this demo, 3 parts are needed: a Curiosity Nano adapter board, an ATtiny1627 Curiosity Nano, and a PIR click board, which is available from Microelectronica. The PIR click board comes with an amplifier for the PIR sensor to ease integration. For this application, the amplifier circuit was removed. By using the integrated PGA in the microcontroller, 2 op-amps, 6 resistors, and 4 capacitors can be removed from the bill of materials, or BOM. The modification instructions and design information are discussed in the application note, linked in the video description. After powering on, the microcontroller initializes the analog to digital converter, or ADC, and the periodic interrupt timer, or PIT. The PIT triggers the ADC conversions via the event system without waking the microcontroller. When the ADC has completed each measurement, the microcontroller is woken up. As a part of the initialization, the PIR sensor and averaging filters go through a brief warm-up cycle to adjust to the environment. The ADC on the microcontroller is initialized in 12-bit differential measurement mode with the PGA. Each ADC conversion is run in burst sampling mode, where the ADC acquires multiple samples and sums them together. This oversampling improves the resolution of the ADC. When the ADC completes a conversion, the ADC result is used to update the averaging filters, which reduces the chance of a false detection event caused by noise in the measurement. There are 2 averaging filters on the device: a long-term filter and a short-term filter. To determine if motion occurred, the difference in value between the filters is compared to a threshold level. If the threshold is exceeded, motion is detected and an LED flashes at 4 Hz. To test the performance of this application, MPLAB Data Visualizer, which is available for free in the links below, is used to plot the data. The red line shows the raw measurements from the ADC, the blue line shows the response of the fast filter, the green line shows the response of the slow filter, and the yellow line shows the difference between the filter values. This application was also optimized for low power operation. After initialization, the microcontroller remains in sleep until the ADC completes the conversion. When the ADC wakes the microcontroller, the clock frequency is increased to improve power efficiency by reducing execution time. After updating the filters and the output of the indication pin, the clock speed is reduced and the device returns to sleep. To measure the power consumption, the Power Debugger kit, linked in the video description, was used. You can find more information about how to set up and measure with this kit in the application note, but in summary, the total power consumption with the sensor included was 13.7 microamps, of which 11 microamps was from the PIR sensor board. This can be reduced further by increasing the biasing resistor, however, this will reduce the output range of the signal. Interfacing low-level analog sensors with the microcontroller is a significant design challenge. In the ATtiny1627 family of microcontrollers, the PGA can remove the need for an external analog amplifier, which saves on the BOM. For more information, please read Application Note 3641 on how to design a low-power, cost-efficient PIR motion detection system, which is linked in the video description. Thank you for watching. Remember to like and subscribe.